All right, this video is a bit of a deep dive into some behind-the-scenes technical observations, discussion. It's a little bit of a departure from the previous videos in that previous videos on the PCUI to date have been mostly around demos of functionality, printing and saving and loading programs and plotting modes and things like that, all the good stuff that we collectively might use the PCI for, PCUI I should say. This particular video is, I'm publishing this mainly because I haven't had any updates on the project in a while, and a few have expressed interest in it and helping me test. So before I send out some boards for test, I want to make sure that everything is as good as it could be, specifically around the hardware. Software, firmware, I could always update remotely. This is remote updatable, or at least through the USB port here. But any hardware changes are costly if once these get out there in the wild. So in the past 5 or 6 weeks, I would say, maybe even a little longer, all was well with the development. All still is well with the PCUI development. We haven't had any major findings that would otherwise undo a lot of the work so far. However, one thing is a little bit of a background. One of the very first models I've built support for the PCUI was this Tandy PC-4. This is a Casio PB-100F, perhaps, because this PC-4 is branded as Tandy. This is the version B, Bravo, of the Tandy PC-4. The prior version, or the original PC-4, was branded as TRS-80 or Radio Shack. So I did all of my testing on this model. I had this model connected to Logic Analyzer. I've scoped and sniffed the bus on this, recorded and captured that, got everything working to what I thought the protocol was. Again, comparing that to any documentation I found online. And it worked. Cassette loading and saving worked. You can see in the demo video recorded a while back. And it printed just fine. And then as I was making PCUI firmware changes, adding some LED status, things like that, I would reconnect and retest old models or previous models that I've worked on just to make sure I didn't break anything. And I pulled this model out of the drawer, and not thinking about it, I plugged it in, and it didn't print at all. It was just all gibberish coming out on the other side. So I thought, wow, I must have broken the firmware. And I just kept troubleshooting and debugging and couldn't really figure it out. And then I said to myself, well, wait a minute, I have 2 of these. I wonder if I really should have connected this version. I wasn't paying attention. Connected this version and it ended up working. So then I went back to this one, which it didn't work, and said, at least to myself, I guess I didn't get that protocol right. So anyway, connected this to the bus sniffer that I have built and the Logic Analyzer, and found quite a bit of difference and a misunderstanding of the protocol completely. Not so much on the high level, but on the low level details, such as the clock phasing, when exactly the signals appear. I had I'll get into the detail of this and how I discovered it. But I happen to record a lot of those troubleshooting sessions, so I won't repeat that in the intro here. So at any rate, got them both working, which is great. And again, these two, this is I'll say the 12-pin connection, which is, you can see that here. And these connect to, for example, the FP-12 or FP-12S, right? So any Casio Pocket computer that's compatible with that printer, putting the PCUI in PB-100 mode here that's just the mode for various, this family of Pocket computers. So that one mode is compatible with various ones. So the PC-4 A and B, or the PB-100 and the PB-100F. I hope I have that translation correctly. Then I came over to the PB-410, which again, just because it has a 12-pin connector does not necessarily mean that it's compatible with the PB-100 mode in the PCUI. It doesn't necessarily mean it's compatible with this. So I looked in the user manual, and sure enough, This whole series, there's others that are similar to this. They're all in the same user guide. This is now compatible. Again, which we'll see in parts of this video. There needed to be some tweaking to get this working. In other words, I further understood the protocol in a little bit more detail after observing this. And then going over to amongst the last in the series, the Tandy PC-5 and the PC-6. Again, they have the same, I don't have the cover off of that one, same 12-pin connector, compatible with the same printer. Cassette interfacing is the same, although there are differences in program and basic capability between these models, but the saving and loading of programs on the PCUI's SD card is similar. So each one of these working, and again, if there's another model that I hear does not work, what I would do is I would connect it to the test harness here and sniff out the bus with the logic analyzer and hopefully determine more specific concrete evidence of how the protocol actually works. So I think I have it now, and through the rest of the video I'll show some of the other discoveries that have occurred along the way and getting there and getting to this success point, and involving quite a bit of change. So one of the things before diving in, this video is kind of in reverse. I have a new connection pack here. So this is a new rev of the board. Functionally it's equivalent, it's just the pinout on the PCUI is a little bit different. There's further explanation on why that is later on in the video. If you're really interested in the technical details, keep watching. So I had a new spin up of the board here, and another thing that I've observed is sometimes the connection, and this is actually working quite well on camera, we could see that these pins are longer up and down in dimension than they are left and right. That is very similar to the original, right? So let's see if I can get this on camera. You can see that it's almost like there are two pins stacked vertically, two pin widths, I should say. The header that I was using, let's see if I can get an older version here. Where did I put it? It was a single stack of pins. Let's see. I don't have one handy. I'll put a picture of it up on the video. But effectively, it worked. It worked in almost all of these models. It's just that sometimes if I move this a little bit slightly, it would not make a good connection, and then you'd either get an error 9 or maybe the loading of cassette wouldn't work. So I have to, again, this is hard for me to find a connector that from a 40, 50-year-old plus calculator, somewhere in the range of 40 to 50 years. Casio likely had these custom manufactured. Perhaps these connectors were widely available back then, but they aren't now. Specifically what I mean is the dimensions of each pin being twice as high as it is wide. These are 2.54 spacing, so that is in fact standard, and the pinout of a single pin header did work fine. The footprint actually worked fine. It's just, it was a little unstable if you move this around. So what I did is I actually stacked two pins together on top of each other in such a way that it's now very close in shape to the original, so it makes a much better connection. And this is quite a hack. It's quite a hack. So I'm still digging and looking around for a more specific type of connector that has the dimensions and the shape that I need. But this does work, and it is rather durable. It just doesn't look that great. So anyway, that was part of the finding of this. And later in the video, I'll describe how I arrived at quite a big finding hardware-wise. So if anybody had any of these, which they don't yet, I would have had to just send out replacements of this connection pack here. So luckily I found that now. So anyway, this new connector is a result of that troubleshooting exercise, as well as a few other things. So right now what I'll do is I'll show some of the testing between each of these models one at a time, and then the last part of the video will be a deep dive into what this rig is, what it does, why I was using it, and how effective it actually was in solving a problem. Okay, so I have the Casio PB-410. This is similar to the PB-100, the Tandy PC-4, etc. And have a little bit of a printing issue with this one. What happens is, if I go to mode 7 and then do some calculations, or I try to run the banner program, I get an immediate error 9. So cassette loading and saving works perfectly with the PCUI. And again, this is the same mode. In the PCUI, the mode that we're using here is PB-100, which symbolizes all of the models that are compatible with the FP-12 printer. So the PCUI, putting it in the PB-100 mode, is effectively saying that it's putting it in the mode to emulate this printer and the associated cassette interface, which is the FA-3 or the Tandy Radio Shack equivalent. So in order to troubleshoot this is a little bit of a behind the scenes of how I reverse engineer the bus protocol, etc., in combination with what others have documented about this this particular series of pocket computers. What I did is I connected the bus of the PB-410 into my my breadboard here. This is quite an interesting tangle of wires. I'm actually quite impressed that this even works. So the bus goes into the breadboard. I then have another connection out of the breadboard over here into a real FP-12 or FP-12S. This is the Tandy Radio Shack model. It's functionally equivalent. And then I also have this logic analyzer connected to the bus and just sniffing on the bus, as it were. So it's going to observe what's happening between the PB-410 and the FP-12. So what I do is I record at around 20 or 25 megahertz samples. I'm using, I believe, 9 pins or 9 I/O points on the bus. And so, for example, I'll go to mode 7, which enables the print option, and then I'll just do a calculation. And I don't have any paper in the printer, but that's enough to put some data out there on the bus, and then for these two, the printer and the calculator, to interact, and then we've captured and recorded that. So effectively what I'm doing is I'm saying, well, what's different between that capture and the capture with a PB-100? What's different, besides perhaps the formatting of the output and the printout? What signaling, if any, is different? What timing, if any, is different? So that is the setup here. And then what I'll do is, after I run that through some scripts to summarize what is going on, I can then make any firmware updates if necessary to the PCUI to accommodate for that. And the reason I have to go through something like this is because not only have others worked on similar printer interfaces, for example, for these, and they've documented what they've observed, that's not necessarily the protocol itself in terms of the specification. So in other words, we don't have a definitive specification for the bus protocol on this FP-12S or FP-12 or any compatible model. We don't have anything from Casio, at least I don't have anything from Casio, that describes that protocol exactly. So if another person has observed, say on the PB-700, which is where I've gotten some of my documentation for, that was an observed result. The timing between the PB-700, for example, and or FX-700, and the PB-410, the PB-100, there could be slight timing variances there, such that if you code specifically off of one observation, if anything is slightly different, in this case, I coded off of the PC5, PC6, which are underneath that printer, you know, 2 versions of that PC4, and then I connect this model and it doesn't work. So anyway, when we look at all those observations together, we could rule out timing differences, or at least identify timing differences between the signaling, for example, chip select and the op signal, operation signal. I suspect that perhaps this model is pulling down one or the other slightly before the other models did. So we're potentially too strict on the printer detection in the PCUI. Anyway, let's see what happens with a firmware change based on the observed results here. Okay, this is one of those rare occurrences where an observation doesn't completely, how can I say this, in the last couple of weeks, I've had quite a bit of trouble with this interface, as we can see in this video and various parts of it. This is one of the very few times in this project where I make an observation with the logic analyzer and it's quite a simple change. Hopefully, we'll see. Got the printer support working. So two things. One, I'll show that here. And two, did I break, while I made it work on this model, did I break it on any other models? That's usually what I end up doing. So let's see. So to demonstrate this, I have the printer mode enabled here, and I can do some calculations, say 1 + 1, and most importantly, we got no error 9, and I'll do that again, but I'll pan over to the PCUI, I'll multiply that by 2, and we could see through the LEDs that we have communication there. I do have this output, usually output to a serial port here or a printer, so that I can see that the printout is working. But just from the status lights, no error 9 here. That is a good sign. So printer support is now working on this model. So one of the other things that I'll demonstrate here, I'll exit printer mode. And what we're going to do is we're going to turn off, see that's error 9 because we're no longer in printer mode. I'm going to load the banner program into this 410, the PB-410. Let's see if I can do that. Okay. And this cable, I've had trouble with this. That's another lesson learned in this project. This is not always the best scenario to test with. So let's see. I wouldn't be surprised if it doesn't load at all. Let's see. Yeah, I don't think this is a solid connection. So what I'll do is I will come back. I'll put the real connector in, and I will come back and continue the demonstration with the real interface pack, and we'll see where we go from there. All right, so we have the correct and proper interface pack for this line of pocket computers connected directly into the PCUI. I would suspect this is not the best setup for various reasons. A little bit of noise, I would suspect. Okay, so we have it connected. I can type load here. I'm going to load the banner program, for example. And over here, I'm going to select banner. And we can see that the program file is loading. You can see the status LED sending. And we've loaded the banner. Let's load the variables next, the bitmap data. So I do have enough variable space to load that. So let's type get. Let's see, I think I called it BANMEM, banner memory, from the special variable A to A52. So we're going to load all of that. And then on the PCUI, we'll select the banner memory. Let's see if that works. Oh, I don't think it did. Let's see. Let's try that again. Okay, so it loaded the variable data. Now, if I hit run, let's put this in printer mode. Let's hit run. We'll do a letter A. And you can see that the PCUI is receiving the printer information here, and we did not get an error 9. So, initial test, very quick spot test here, smoke test, whatever you want to call it, seems to work. That's a thumbs up on that version. Okay, so let's move on and make sure we didn't break support for the PB-100, version A, version B, the PC5, the PC6. We'll go all the way down the line there and just make sure we didn't break anything. Okay, so I've connected the PC4, version A. This is the unit that gave me the trouble that completely, as we know in this video and earlier sections, had to rewrite the entire protocol. Okay, so I connected it to the same interface pack. We're in printer mode. I've enabled the print output here, and I did some very basic calculations, and no error 9. So I could divide that, for example, by 2, and then we'll see, yeah, great. And we'll also see maybe if I have the banner program in here, we'll give it a try. And so we can see we have good communication. Let's wait till it finishes printing. No error 9. Thumbs up, we didn't break it. So this is the first time in the history of my project here working on this where the change was so simple and it didn't break anything else. So yeah, okay. That's a problem solved with the PB-410. So that's going to be one of the concerns I have with the PCUI project, with at least this protocol, because again, like most of the other pocket computers like the Sharps, I don't have definitive timing diagrams, specifications, protocol specifications official from either Sharp nor Casio, and I wouldn't expect them to publish that. And besides, these are 30, 40, 50 years old, some of these calculators. So anyway, because I don't have that specification, I'm working off of observed behavior, with the bus being observed. And if anyone watching this video has, in the future when I release this, a PCUI, and it doesn't happen to work with a specific model other than the ones that I've guaranteed compatibility with. For example, let's say there's a PB-420. I'm just making that up. There may or may not be. I've tested it with a PB-410, seems to work fine. The PB-420, let's say in the user guide it says it's compatible with the FP-12S as well. If for some reason there's any timing variation, I really have to get my hands on a PB-420 and tweak, again, the protocol in such a way that, again, every variation gives a better understanding of the protocol. So I would think with the 5 or 6 models I've tested with this particular interface that I would have seen it all. But the 410 definitely threw a curveball. Anyhow, this is a success. All right, now this model here, the 2nd generation PC4, PC4B, as opposed to the prior version of this, just a newer revision, slightly more basic commands. Some of the shortcuts above the letter keys are different, but otherwise, same printer, same cassette interface. So let's test the printer first. We'll put the PCUI in printer mode. We have it connected, and then I'll hit mode 7. We'll do 1 + 1. Keep it simple. Let's say times 6. And we see successful communication. No error 9, so I will turn off the printer mode. Let's try loading a program. Oh, I didn't turn off printer mode here first. That's a problem. Okay, good. So let's type load here. And we'll select the banner program. And it looks like it's working. Okay. And we'll load in the variable data for the banner program. Okay, and we'll go back on the PCUI. We're going to select the banner memory. The header's displaying. That worked perfectly. So let's run it. Put this in printer mode. And we'll do a quick test with the letter A. And it looks like we have good communication. No error 9. That's a successful test. All right, here is the Tandy PC-5. I'm probably going to get this wrong, but I think this is equivalent to the Casio FX-780, perhaps. I'm not too sure. But this is the Tandy Radio Shack version, so this is the PC5. It was short-lived. It was only available for a year, so these are somewhat rare. I have the PC5 connected to the PCUI, and PB-100 is the model of pocket computer of the family that these all belong to, the FP-12S mode here for the printer, for example. And so I'm going to put this in printer mode, and I am going to go to mode 7, and that's going to turn on the print icon. So I should be able to do some calculations, and no error 9, and I'll do the same thing as I pan over to the PCUI, and we could see successful communication. So the printer support works, which is great. Let's go ahead and try to load a program. So I will clear this out. I'm going to load a PB-100 program. This may or may not work. I have no idea. First lesson is take it out of printer mode first. Okay, let's try that again. Try load. And then on the PCUI, oh, I got an error 9. Oh, I'm still in printer mode. Let's try that again. There's a lot of glare on the screen. So now the PCUI is presenting a menu for what to send. We'll send the banner program, and you can see the header is being displayed. The PCUI is sending the data, and the cassette loading is successful. Now, the banner program I happen to send is for the PB-100. I have a different banner program specifically for this model, so I will load that from tape, because I have that on my blog. I posted this a while ago. I'll get that loaded into here. I'll then save it into the PCUI so that I have a PC6 version of the banner program. And then I'll test that thoroughly. So initial test looks good. I'm able to load from cassette. I'm able to print with the PC5. Okay, this is the PC6. So this is the, I believe, the Casio FX-790, perhaps. I'm not sure. There's too many models to remember. Let's try loading from cassette. So I have this connected to the PCUI. So we will load from here. Okay, I'll try panning over to here. And let's see if we got it working. Yep, okay. Success. So let's try mode 7 to turn on the printer. At the printer icon, we'll put the PCUI in printer mode, and we will calculate something advanced here. Okay, no problem there. Let's see if the communication's happening. It is. No error 9, so still compatible with the PC6. All right, now the second half of the video, it's a little bit long, longer perhaps than the first half. So if you're really curious what this mess is here, how we arrived, or I arrived, we, PCUI, myself, all of what's going on here, these guys, stick around. I'll go over in depth a little bit, get a little bit technical as to what's going on there. So I already posted a video earlier on the PB-100, which is the Casio model that this is based on. Tandy Radio Shack had Casio build their PC4, which is effectively the PB-100. And while I posted that video, the printer and cassette interface was working just fine. But that was actually on this model. It's also a PC4 from Radio Shack or Tandy. However, the badging on this one looks a little bit different. This one is badged as a Tandy Pocket Computer PC4, and this one is badged as the Radio Shack TRS-80 Pocket Computer. It is a PC4, same amount of memory out of the box. The keyboard layout's roughly the same, just some of the hotkeys are a little bit different in terms of the labeling up here for the secondary functions. This model is actually newer than this model. So Radio Shack released this one, which is the PB-100, and I believe the next year, maybe 2 years later, I can't recall exactly, Tandy had a version B of this particular model, which I believe maps over to the Casio PB-100F. I'm not 100% certain on that, but anyway, this is the version B, and then this later became known as version A. So Tandy was selling the old stock of the original PC4 with the label A. The catalog number had an A after it, and then the new version had the B version. This version has a few more basic commands supported over the other one, but my work was on this model, and I got the printer interface working perfectly and the cassette interface working. And some time had passed by, maybe months, and then I connected this version. I was testing something. I can't remember what really made me go about testing that again. And it didn't work. The printer support, it was just all garbled data. It just wasn't working. And so I thought maybe I reverted something in the software on the PCUI. So I connected it to this version. I looked carefully at the video, and because I put both of these back, and I didn't really remember which one I had tested with, and found out that I was actually recording the video, the demo, and doing all of my hardware and software development on this one, looking back at old pictures and things like that. So when I connected this one again, it worked. And then I connected back to this one, and it didn't work. And you know, at first I'd written it off as, well, maybe there's something wrong with this one. Maybe there's a pin or something that's not making a good connector. I mean, after all, look at this. This is crazy. Of course, I didn't have that connected. I actually had a real interface pack connected. So this is what the interface packs look like. They plug directly into the pocket computer, and then the ribbon cable plugs in the other side. But again, this isn't an original OEM connector. The connectors on these are slightly bigger, slightly wider. So I had written it off as really potentially a hardware issue with this particular model. And then, out of curiosity later on, as I worked through different models and support, sorry for the finger in the way there, I got this out of the drawer here, a PB-410, and this one also didn't work. So I then connected both of these models to the real printer that I have, the Radio Shack equivalent. So this is equivalent to the Casio FP-12. And I do have a proper cable for this, and it worked just fine. This model worked. The one that didn't work with the PCUI worked fine. And this model that didn't work with the PCUI worked just fine with the real printer. So that got me thinking that there may be some folks that want to use the PCUI with this model, this version, or the PB-410, or some of the other models that share the same printer that supports multiple models. So I started debugging the code. I originally had done all of my PCUI development with this $8 to $14 logic analyzer. You can get these on Amazon. They are very inexpensive. They do work. There's nothing wrong with this particular model. Your leads connect here to the device under test, and then you connect this to a standard USB port on the computer, and there's a lot of software that different versions you can use, but this worked fine, I thought. And it actually was not good enough. This goes up to, I believe, 10 megahertz roughly, or 24 megahertz. So I wasn't able to get the resolution that I needed, or I questioned whether or not certain events were occurring when I thought they were. And the idea is that this is connected between the pocket computer and the PCUI, or the pocket computer and the real printer, and you can inspect what's going on the bus and then reverse engineer it. And there are some folks that have documented how this interface works, and even provided some sample source code, which again proved with the inspection through this, with some sample code that I found that others have done on their own a while back, ended up working fine with this model. So it was a valid attempt, but it was not accurate enough really to work with other models. So it was very timing specific, driven by delays and certain frequencies, speed, that kind of thing. So I ended up questioning the logic analyzer and then purchasing a slightly more expensive, I'll post links to these devices in the description. I can't recall the name of this, the name brand, but on Amazon, this is roughly $190 at the time of this recording of this video. So a little bit more expensive than the $12 logic analyzer. And the reason I purchased this one is because I was looking for something that would do at least 50 megahertz. So at least double the resolution of this logic analyzer here. Maybe 100 megahertz would be great, 200 megahertz even better, but again, I think that would be a little overkill for something like this. Now the bus speed on these models is specified at 200 kilohertz. That's very slow. And I would have thought that a 25 megahertz logic analyzer would be sufficient. But the issue, I think, was in noise on the bus, and I think the issue was also timing of when data would be available on the bus, and getting very specific. So anyhow, I purchased this logic analyzer, I hooked it up to the device under test, and through the increased resolution here, I was able to solve the problem, which I'll get into a little bit. So the way that these work is, I explained earlier, but these leads, most of these logic analyzers, we'll talk about how many channels they have. So this one has, let's see if I can get that right, 8 channels, channel 0 through 7. So you could read 8 different signals at once, signal lines. This particular model has, let's see, I think it's 4, 8, 12, 16 different logic lines at once. The bus interface on these requires 9 pins. So 9 different signals or bus lines need to be monitored for effective debugging. So 16 ports is a little overkill for my project, but again, it's good to have. And the way these leads connect is they have kind of the same jumper DuPont style. You can put these DuPont type connectors directly into the leads. So each of the probes, so you have 4 of these connections per port. So you have 4 blocks of 4 on this logic analyzer. So each one will have its signal line and then a dedicated ground line here. And so while this is relatively low speed, I didn't hook up all of the grounds, just one of them. So I hooked this logic analyzer up, and I connected this printer, this pocket computer, and the logic analyzer. They're all on the same bus. And what I did on the software is I'd hit record, then I'd go onto the pocket computer and print something out. And it would print to the printer, but all the while this was capturing what was going on the bus. So immediately, as soon as I hooked up the connections, the screen on this pocket computer would dim pretty heavily. And so that's kind of a sign that something electrically is going wrong. So I was just connecting the leads to the bus, and I was unable to do that. Now I don't, again, this is a very weakly driven output connection here on the bus, meaning it's effectively a calculator, so it's not going to be able to drive the bus very hard in either direction. So I suspect when hooking this logic analyzer up, it was loading the bus too much and pulling too much current out of the bus here and dimming the display. I mean, after all, this runs on two double, what is it, CR2032, a double coin cell battery, two of those coin cell batteries, so it doesn't really have that much power to work with here. So I ended up thinking that we have a problem. I can't even really measure what's going on the bus. This sometimes would do the same thing. The USB ground, by the way, this USB ground is the same ground as my board, which is the same ground as the testing I'm doing here, which is the same ground as the calculator. So it wasn't a floating ground issue. And sometimes I found this didn't work either, and I never really solved it. And other times it would work fine in terms of whether or not it was loading the bus down too much. So at any rate, the solution really is recommended to when you're hooking up the logic analyzer if the device under test, it can't really drive the bus that hard, or if this is interfering with the bus. What you can do is you can put a buffer in between the logic analyzer and the bus itself. So what I ended up doing was connecting a buffer between, like I said, the logic analyzer and the pocket computer bus. And the reason I was able to do that with relative ease is because the buffer that I'm using on the PCUI, this buffer here is a 16-bit bidirectional buffer. It's not that unusual to have these. However, this one is a dual level converter. So the Pico runs at a CMOS level, and many of the pocket computers, most of them run at a 5-volt TTL level, which means you can't connect the calculator directly to the Pico or vice versa. I'm going through a buffer that can convert not only buffer direction, it can tri-state and remove its presence off the bus. It can also translate between the two different voltage levels. So half of this IC is powered by 3.3 volts. The other half is powered by 5 volts, so that it can convert the logic ones on each pin of the bus all at once, obviously, meaning you can't have some pins at 5, some pins at 3.3. So this side, the entire side, all 16 pins are at 5-volt level, and then all of the pins over here are at 3.3 level. You can change half of the chip in one direction and the other half in the other direction. So you can do 8 bits as inputs, 8 bits as outputs, all 8 or all 16 as ins, or all 16 as outputs. So you can't flip each bit or pin direction one at a time, but you can flip half the chip one way and half the chip the other way. Same with the output enable. So you can output on 8 pins at a time, or the entire chip, or nothing, none. So it's a rather flexible integrated circuit here. So before I actually chose this one, I ordered one, and in order to breadboard it, I put it on one of these adapters that converts the, it's hard to see this with this camera here, but it converts the surface mount pinout or pad footprint here to a DIP or dual inline package, where you can pop that into a breadboard. and wire it up and test it. So I ended up doing that. I didn't throw this away when I was done. I kept it. So I figured, well, if I need a buffer to go from a logic analyzer to this bus, I can just reuse this. So I did. I plugged that in. And the way I have this configured is that the logic analyzer side here is connected to the output of this. So this is going in this direction. So I've hardwired this to be output enable is on all 16 pins, and the direction is this way. So that anything going on in the bus is going to be directed to the logic analyzer. And this side of the IC I have set to 3.3 volts. So technically this is a logic analyzer connected to a 3.3 volt or CMOS level bus. On the other side of the IC here on the buffer, I have there's 9 pins on this bus, this Casio PB-100. I have these 9 pins as inputs, and they're connected to the bus. So this over here is my attempt at creating a bus that I can have multiple things connected onto. So effectively, this chip is isolating that logic analyzer from affecting the bus in any meaningful way. These are, the pull downs or pull ups for controlling the direction and output enable. It's also a good idea when working with this particular IC to pull down any unused inputs to ground. So that way we're not drawing current through the unused inputs. You don't want to let them float. So that's why a lot of these resistors are tacked in here. So that's the configuration in order to, and of course this was connected here like this, so I can remove, it's going to be hard to see, but there's actually a header here. I can remove this and plug it into here. So I can switch between models fairly quickly. And I can also connect this to the bus if I wanted to. So I have this connected here. So if I want to take a trace of the real printer FP-12 to the pocket computer, I can do that. I could also take captures with the PCUI and the pocket computer as well. So that was kind of the stumbling upon why perhaps I'm not getting a full picture of the bus, stumbling onto the solution. It ended up being just inadequate test equipment, really. And looking back at which I'll share here, of what you see with the logic analyzer, it's really fairly straightforward. The difficulty really is understanding what the bus protocol is and when a particular device is driving the bus. So the idea behind, if you're curious how these really work, the calculator versus the printer, if these two are connected, if you're not printing anything, then you really can't have the integrated circuit in here interfering with the bus here. The way this calculator is designed is that these 9 pins there's 4 data lines and some clock signals, chip enable or chip select. There's internal operations that are happening in the calculator just when it's running, just when it's on. And if you're typing or running a program, you're going to see that on the bus. So this has to effectively be isolated from the bus if there's no printing going on. And the way that that's done with many of these systems, even today, most bus architectures have what's known as a tri-state mode, meaning tri-state effectively means it's disconnected. And so this will listen for a printer command, and when it receives a printer command, it then grabs onto the bus and will effectively grab the bytes out of the calculator. That's the other thing with this particular model, these Casio models that support that printer. The printer, the calculator or the pocket computer does not put the bytes to print on the wire for this to listen for and print out. This is very strange in that when you print a character, the pocket computer puts half of that character, it's a 4-bit bus. So that the 8 bits have to be divided into 2 4-bit nibbles. So it'll place the first nibble on the bus, or actually doesn't place it on the bus. I should be very clear here. It puts the nibble in memory, this 4-bit memory here, at a specific location. And the printer will receive, when the calculators put that nibble into that location in memory, the Pocket computer signals out on the bus that a printer byte or nibble is ready. This printer listens for that, and when it receives that or picks up on that bus pattern, this will then tri-state. It disconnects from the bus. This becomes the bus master. It then grabs onto the bus and then instructs the memory in the Pocket computer to perform a read operation. It then reads the 4 bits out of memory. It then auto advances to the next memory address. So the calculator technically put both nibbles in 2 memory locations that are sequential. It then grabs the second half of that byte. After the second half, it signals to the Pocket computer that it's done. It releases the bus, so this tri-states, and then this becomes the bus master again, and it grabs a hold of the bus and continues on. So that repeats for every character that needs to be printed. So effectively, this needs to listen onto the bus, or listen on the bus for a specific event to occur. Then it grabs onto the bus and actually pulls the data out of memory, out of the Pocket computer. So that is extremely difficult, at least in my opinion, to choreograph and get right. And so when you're looking at a logic analyzer, the trace looks, and I'll kind of review this real quick, but here are the 4 data lines, D1, D2, D3, D4. This is a 4-bit Pocket computer. And so, you know, your data lines are here. It's a biphase clock, so there's a clock. They run opposite phase of each other. And you have your chip enable, 2 chip enables here. So when printing, it's chip enable 1, which goes low, and there's an operation command. So a 0 or a 1 would mean a read versus a write, for example. I'm oversimplifying this. And then there's a clock, and the clock is what both devices will, they'll latch onto that clock. So let's just say, if you look very carefully, this is where the logic analyzer, the higher resolution, is extremely valuable. These data lines do not all appear to flip at the same time. Sometimes they do, right? This is the operation, the op line, and this is D1. They're not necessarily in phase here, and neither is this clock. So this clock is cycling here, and these are happening after that, for example. These lines appear to be falling at the same time to, to a low level. Here, a low level really means 1 on this particular Pocket computer. So the lines are floating, not floating, they're pulled up by weak pull-up resistors. And so when a device pulls the line down, that signifies a 1. So this is really an F. If we look here, this is 0, 0, 0, 0, which means 1, 1, 1, 1, and that's an F. So anyway, the higher resolution really gives you a picture into what clock phase, which clock line, was it 1 or 2, at which phase. So this is opposite phase. You could see when one's high, the other's low, etc. You could tell the duty cycle of the clock. It's fairly accurate. The frequency of the clock is a little fast at 215 kilohertz. And you can tell exactly when, so after 1 complete clock cycle, for example, and only 1. So you don't want to trigger on the falling edge here or the rising edge here. Maybe you could. But you do have for example, one more clock edge that you could safely grab the data or sample the data on. So if you did that on the falling edge here, you're going to see a 0, 0, 0, 0, right? Let's see, no, actually that would be losing my line of sight here. That's D1, so that would be, that'd be effectively a 0, 0, 0, 0. But if you were to sample here, you'll see the real value, which is an F, 1, 1, 1, 1. So Having the higher resolution definitely helps see that. Otherwise, you're just going to maybe see all of these happening roughly at the same time. Maybe it would appear that these could all line up together. Again, probably a bad assumption to use the first clock cycle here. But more importantly, you can see the noise. So we can see what appears to be the bus owner changing. That's what it looks like here. So you see a nice smooth clock here. You then see something, maybe a transition happening where one device is letting go of the bus, the other, it's floating for a while, then the other grabs a hold of it, and there's a lot of settling time here. The clock would never run at that speed, for example, which that's 1 megahertz if that was the case. So you can really see that, and it helps filter out the noise that you might be seeing in software. The Pico runs at an incredibly fast speed at state machines, so it is entirely possible that it's going to catch an edge of an input here when it's not really valid. And as it turns out, that's exactly what was happening. Not only that, but if we zoom out, this is a printout, a capture of printing a line of, I believe Hello World is this example, but each one of these would be a character, or a series of characters, really. So this might be hello world, it might be multiple iterations of that. So anyway, this is what you get during a logic analyzer probe connected and you're recording. One lesson learned here is that when I first hooked this up, I was stuck at 25 megahertz. Again, it seemed to be no better than the old logic analyzer, and I finally read the manual. And with logic analyzers, the reason why many of them, the less expensive ones, are limited to around 25 megahertz is because they are streaming the capture data over USB, and you can only go so fast over USB without any sort of buffering. And as it turns out, the more expensive logic analyzers have more memory for buffering. And so if you put the operation not in stream mode, but if you put it in buffer mode, turn off the number of channels. So for example, if you're only using 4 channels, you can go up to 400 megahertz. But since I need 9 channels, the maximum I can go is 100 megahertz. It's just a function of memory here. So the more expensive the logic analyzer, the more memory it's going to have for buffering, the higher the sample rate could be with the higher number of channels at the same time. So that was a lesson learned. So putting it in buffer mode, I could easily do 5 seconds of a capture. Actually, it looks like it'll even do 50 seconds. But that's kind of misleading. So if I do 5 seconds at 100 megahertz, it'll sample, and then it will go ahead and I'll just turn this on, actually do a live example here. I could hit the start button, and it can do a maximum of 5 seconds roughly. But that 5 seconds, when it's over, it's going to then push the data over the USB channel and then into the software so you can view it. Now, if there's a lot of bus activity, such as you trash the bus, which I've had happen many times with this, that sampling window of 5 seconds will shrink dramatically rather quickly. So it's not really a function of the time, since it's using RLE encryption, RLE or run length encoding. It's a form of compression that's lossless, and so it can compress, in other words, only record state changes. So in a normal slower bus of this type of calculator, you'll easily get 5 seconds. If you start rapidly changing a lot of inputs, then that buffer is going to be eaten up inside the logic analyzer, and you'll get less time that you can record. So this is normal bus activity, and zooming in, you can actually see every key press, every memory read, every memory write that's going on inside the pocket computer at idle here. So anyway, this was kind of a really an eye-opening discovery. Using test equipment that is high enough resolution for the device that you're working with is an absolute must. Again, unless you have documentation that is very clear and very precise, all you have to go on is observation. And if your observation is a less than optimal resolution, while you're accurately coding to what you're seeing is not necessarily what's going on the bus. So increasing that resolution gave me a bigger window into what's happening. So at the end of the day, both of them are now working with the PCUI. By the way, the old iteration was working heavily on timing and delays. The new version for this particular model, or these particular models to be more generic, is based on actual bus sampling rather than timing delays. So for example, if one calculator runs a little bit faster than another in terms of the model or the version of the ROM or the hardware, the Pocket Computer Universal Interface will rely on the actual clock, and it'll count the clock cycles that are occurring, and it actually latches on the appropriate edge. So rather than relying on timing, it is actually relying on what's really going on the bus. So if the protocol says that the data is ready on the second rising clock edge or the second falling clock edge, that will not vary by model, because the printer is unaware of what model it's connected to. There's no model handshaking here in terms of which version of the ROM. It is operating under very specific specifications, and I suspect now the PCUI is also operating under more strict specifications and following that protocol more closely. So that eliminates the timing component between the old version and the new version. And perhaps on later revisions also, like some completely different model, such as a PB-410 that uses the same connector. This also works with the Tandy PC-5, the PC-6, which is Casio FX-770, for example. I have the Radio Shack versions. They're this clamshell design. They take the same connector. It's the same bus protocol. So again, it was really important that the timing and the bus protocol were followed exactly right on the PCUI. Otherwise, it's not going to work. It's not going to work in the same way. This one model of printer worked with all of those various models of pocket computers. So I was under the strict kind of the goal, under a strict goal of doing the same thing here with the Pocket Computer Universal Interface. So that is how I got it working. And the one thing I'll share is usually what I do with these is to really hone in and fine tune these to make sure that these models are supported and not just kind of a fluke or it's mostly working, and on occasion there's a glitch or two. While that still happens on occasion, what I usually do to try to mitigate that is I'll run programs like this one here, just Hello World, and it is a basic program that just loops over and over and over again. And I'll let that run, for maybe 20 minutes, 30 minutes, maybe different configurations of that, longer strings, shorter strings, to try to really see if the protocol is reliable. Do I have anything going on the PCUI that could be interfering? Interrupts happening at the wrong time, long delayed screen writes, things that, if you just casually print something out, it seems to work and you write it off as functional. It really has to be stress tested. And so if I see Hello World being printed for 15 minutes constantly, or maxing out the lines of characters being printed, it's safe to say, and then do that same test on every model that you have, it's safe to say that the support is working well. One thing to note here, I did notice that the real FP-12, or the real printer, because again, this is thermal, and this works. I posted another video on the Sharp version of a printer that's similar. So there's a thermal printer head here. The Sharp works in the same way. It prints from left to right. And what happens is, at the end of the line, the print head has to return back to the left, and it's not printing when it does that. So you have a long string of characters being printed, and then a slight delay as this returns back, and then it can continue on. So the Pocket computer, from its perspective, because of the handshaking that's going on, the printer will signal that these printers do not have a large buffer. They probably don't have a buffer at all, I'm not sure. Maybe 1 byte, and that's it. So the printer is not going to signal to the calculator that it's done and it's ready for another byte until it's moved the print head over and it's done printing that character. And at the end of the line, it's certainly not going to signal that it's ready for another byte until the print head moves back to the left and it's ready to print the next character. So this was printing very, very fast. In fact, when I looked at the screen, this is just the PCUI is connected to a terminal program. So this would have been sent, or could just as easily be sent to a real printer, but I don't want to waste that much paper. So I have it connected to a terminal, a serial terminal here. And effectively what that allows me to do is see what's being printed, and I can see the speed. The baud rate here is, I think, 38.4, so it's much faster than the printer here. And it was printing fast, and I thought to myself, wow. And I'm seeing a little bit of corruption. Again, I posted a video on the Sharp 1401, I believe it was, where it was printing quite fast, much faster than the real printer. I didn't really notice that right away. And it was on occasion corrupting or missing a character. In the case of the Sharp, it was trashing the entire line, and then it would sync up eventually, and so you get a whole bunch of gibberish printing out. And on this model, it was just dropping a character on occasion. So, you know, every 30 lines or so, a character would be missing. But I know, again, because of that Sharp experience with the Sharp model, I said, well, this is printing way too fast. It still is, actually, in my opinion. I think it's printing a little too quick. So maybe the firmware and the you know, calculator can't handle that kind of speed. You know, it wasn't really the real hardware that Casio produced to go with this. So I intentionally added the same delays that I was seeing on the real printer, the same delays after each character and the same delay after a carriage return, to try to simulate a slower pace so that we're not, you know, pulling characters out of the calculator too fast. Because believe it or not, I'm sure the engineers, software engineers, knew that this printer is slow to return after each line. So that could be time that the calculator or the pocket computer uses to do something, some housekeeping inside the machine. So without that, on occasion, it would drop characters. So that's just another example of kind of the thinking that goes into some of these reverse engineering efforts here. So Hello World is working just fine. I think I left it running for maybe a half an hour and didn't see one glitch. So I'll repeat the same test on this model. I'll repeat the same test on the PB-410 and some of the other models that I have, the PC5, the PC6, and whatever other models use the same printer connection. Now the other lesson learned here, which is, this is a difficult one. While I was doing my testing on this model, I didn't really pay attention to which pins on this buffer that I was going to connect to which lines on the pocket computer. And I made probably one of the biggest hardware mistakes is I didn't separate my inputs and outputs, or who controls what on the bus at what time. In other words, I designed the hardware first, and I mapped this interface pack to certain GPIO pins and therefore certain pins on the buffer to certain pins here. And what effectively happened was I was unable to drive the bus in you know, reading from the data lines at the same time as, look, we see an error here. So that'll have to be looked at. So after printing for a while, we have an error 9, which is a error in the printer. So a little bit more fine tuning on the delays is what's needed there. So anyway, the hardware had to be changed, which effectively doesn't mean that this board has to be changed, but this interface pack just needs a pinout reassignment. So there's another version of this board that is going to be required to properly be able to support the bus protocol here. So glad I ran into that problem with, you know, some variation in these models now, rather than too many of these getting out there. So these are relatively inexpensive to make, so not a big deal there. But that was a lesson learned. So that is an update on the PCUI and, you know, some of the you know, the trials and errors, so to speak, that goes on with testing the various models. And I will be posting a firmware update once I get this exactly right. I want to be able to run the Hello World program for at least 30 minutes or so on every single model without any errors. and then I'll call it functional at that point, and then I'll update that interface pack accordingly. So that is it for this video. Thank you for watching.